Hi, this is a lesson about SHM graphs, and this video should be watched after you watch the previous one for this lesson. So I have in front of me a page from your booklet. This is page 7, and I've just drawn a few things onto here. So the first thing are these are reference circles, and these are your x and y axes, and there are 3 of those. So one of them is to draw a displacement time graph to see what it looks like. The second one's velocity time graph, and the third one is an acceleration time graph. And I've got it's all color coded, so I'm going to use red for the displacement time, it's rolling, blue for the velocity time, and green for the acceleration time graph. Okay, so the first thing we do is divide the circle into 8 quadrants, and this is for when timing starts at the rest position. So that's the equilibrium position, and what's happening is the reference particle is moving anti-clockwise in a circle, and in that time your simple harmonic motion particle goes from equilibrium all the way up, back, all the way down, and back. And let's assume this takes 8 seconds for simplicity's sake. So at time 0, your reference particles here and your simple harmonic motion particles are equilibrium. So I'm just going to put a dot to see where that is. 1 second later, your reference particles moved here, your simple harmonic motion particle is going to be there, and I'm so just going to put a dot where the simple harmonic motion particle is going to be 1 second later. After 2 seconds, the reference particle continues on its way up and it's right on top. The simple harmonic motion particle is also at maximum displacement, which is the amplitude. This reference particle continues in its circle, and what happens when it moves this way is that it's coming down, so the simple harmonic motion particle is now on its way down, so it's going to be here. After 4 seconds, the reference particles here, the simple harmonic motion particles at equilibrium but moving downwards, so that's at equilibrium. The reference particle continues to move, and at 5 seconds it's here, and your simple harmonic motion particle is somewhere there, so that's where the dot comes. After 6 seconds, your reference particle is right at the bottom, your simple harmonic motion particle is at the other end of its oscillation. 7 seconds, your reference particle is going this way, your simple harmonic motion particle now starts to move up and it's here, and at the end of 8 seconds it's completed a whole cycle. So if I join all the dots, see what I get, you end up with a sine curve. Now the length of this phasor, your displacement phasor, is the amplitude. Okay, so you actually get, and your displacement at any instant is y, and that's how we get y equals a sine theta or a sine omega t. Okay, so that's how you get that equation which we derived earlier. Okay, similarly for velocity, I've taken my blue pen. Your maximum velocity is a omega. Okay, and so this we're going to plot a velocity time graph for the second one. And your reference circle, now when your reference particle is here, its velocity is actually a tangent to the circle pointing upwards, and the velocity of this is a maximum of your SHM particle. So it's actually, because it's pointing upwards and I have to draw a phasor, phasors are rotating radius vectors, so I've got to kind of put it here. Oops, my pen's fallen down. 1 sec. Yeah, okay, here we go. So this is your velocity phasor, and the length of your velocity phasor is a omega. So that's where it is at time 0. After once, so this is my 0, 1, 2, 3, 4, 5, 6, 7, and that's your 8. So if you just trace your way down, so after 1 second, that's where it is. 2 seconds over here. 3 seconds it's coming down, 4 seconds all the way down, 5 working its way up, 6 going through equilibrium on its way up, 7 it's here, and 8 it's right at the top when it's at the other end. So now when I join these ones, I end up with a cos curve. So I have velocity at any instant of time is a omega, which is the length of your velocity phase, or cos omega t, or cos theta. So that's my equation for velocity at any instant of time, because theta is omega t. It can also be written like this. Okay, and now I'm going to pick up my green pen for acceleration. This is the last one. So your acceleration is, even when the SHM particle is here, or when the reference particle is at equilibrium over here, it's actually pointing towards the center of the circle. And like I said, because it's pointing to the center of the circle, I've got to have the tip of the arrow here and pointing here. Okay, and the length is a omega squared. So that's my time zero, and you just number 1, 2, 3, 4, 5, 6, 7, and 8. So time zero, it's here. After 1 second, it moves this way. Okay, so after 1 second, it's here. 2 seconds all the way to the bottom. 3 on its way up. 4 through equilibrium. 5 on its way up. 6 right at the top. 7 coming down. And 8 over here. So when I join all these dots, I'm trying to do this all with one hand without the paper, you end up with, this is called a negative sine curve. So the acceleration at any instant of time is minus a omega squared sine theta. Also, this is the same as a is equal to minus a omega squared sine omega t. So those are the equations for simple harmonic motion for instantaneous displacement, velocity, and acceleration. So it looks like that. Okay, thank you.